Alrighty, so now we're going to talk about something called formal charge. Formal charge is the charge that would reside on an atom in a molecule if all of the bonding electrons were shared equally. So if each um, atom in the molecule or the ion was claiming all of those electrons as their own and sharing equally. All right, so the formal charge is calculated based on the Lewis structure. So the first step is to draw the Lewis structure. I wouldn't try to calculate formal charges without drawing the Lewis structure. You need to have the structure first. All right, next, this is our equation. So the formal charge, this is in your book, the formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So you look at all your lone pairs and there's 2 non-bonding electrons in each lone pair. So that's the number of non-bonding electrons. And then 1/2 times the number of bonding electrons. So you can definitely try to remember it this way if you want, but I like to do it a little differently because it's one less step that you have to do. So what I like to do is to use the number of valence electrons and the number of non-bonding electrons. So just counting those dots around each atom. So calculate the number of valence electrons from the periodic table and then subtract the number of non-bonding electrons by counting the dots around the atom, if there are any. And then just subtract the number of bonds attached to that atom, because the number of bonds is equal to 1/2 the number of bonding electrons. So the reason we do 1/2 the number of bonding electrons is because there's 2 electrons in a bond. So then we have to do half of that to get the 1 electron that is associated with that atom. So I lied when I said up here that if all of the atoms in the molecular ion were claiming them as their own. That's not what I meant. I should not have said that. I mean the charge that would reside on an atom if they were all sharing equally. If we could divide those bonding electrons equally in half and give half to one of the atoms and half to the other. That's what I meant. Okay, anyway, so that's what happens. The number of bonds so whatever number the bond is, there are 2 electrons in that bond, so that makes up the number of bonding electrons, and then you have to multiply it by 1/2, whereas I think it's easier to just use the number of bonds because it's the same thing. So if you just use the number of bonds, you count the bonds, then you don't have to multiply by 2 to find the number of bonding electrons, just to divide it by 2 again to get 1/2 the number of bonding electrons. So I prefer this second way, but you can do whatever makes the most sense to you. Just make sure that you are being consistent and that you're getting the right answer. Check your answers. So do some problems where you know what the answer is to check and get used to the strategy. All right, so let's look at some molecules. So for example, this is the boron trichloride molecule. So boron with 3 chlorine atoms, and this is its Lewis structure. So boron on the periodic table has 3 valence electrons. Each chlorine has 7, so there's 3, so that's 21. So there should be 24 electrons in this structure if we want to check. There's 6 around each chlorine, so that's 18. And then there are 3 bonds, so that's another 6, so that gets us 24. Yep, so this is the right Lewis structure for this molecule. And if we split those bonds in half so that we can see that there's 2 electrons in each bond, that's how you would want to do it if you're doing the 1/2 method. But now we're going to calculate the formal charge. So chlorine had 7 valence electrons. There are 6 non-bonding electrons on each chlorine because it has 3 lone pairs. And then there is 1 bond, or 1/2 times 2 bonding electrons between it and boron, if you want to do it that way. But basically, there's one bond, so there's one electron associated with chlorine that's in the bond, and one electron associated with boron that's in the bond. So boron has valence electrons, 3 valence electrons. It doesn't have any lone pairs on it, and we'll explain why in a later video here. So that's a 0. And then there are 3 bonds between boron and the 3 chlorine atoms. So 3 bonds, we subtract 3, we get to 0. I guess I didn't do the whole thing up here. So it was 7 minus 6 non-bonding electrons minus 1 bond gave us 0. So both of these atoms, well, technically all 4 of these atoms, because all 3 of the chlorines are the same, but all of these atoms have a formal charge of 0, which is good. The sum, and I'll explain why that's good in a little bit, but that's what we want to see, if possible. So that's how you calculate formal charges. Another thing to note is that the sum of the formal charges for all the atoms in a molecule or an ion is equal to the charge on the molecule or ion. So if it's a molecule, the sum of the formal charges is 0. If it's an ion, the sum of the formal charges is the charge on the ion. All right, so let's look at carbon dioxide. So we drew the Lewis structure for carbon dioxide in the previous video. And that means that the carbon dioxide molecule has 2 lone pairs on each carbon and a double bond between carbon and each oxygen. Okay, so let's calculate our formal charges. So for the 2 oxygen atoms, they have the same bonding, so I'm just going to calculate it once. So we have 6 valence electrons in oxygen, because it's in group 16. We have 4 non-bonding electrons. Just count up the dots. There's 2 lone pairs, so that's 4 non-bonding electrons. And then there are 2 bonds between carbon and each oxygen. So that's 2 bonding electrons in there from the 2 bonds, because we take it in half like we did up here. Anywho, so 6 minus 4 plus 2 gives us 0. So the oxygen atoms have formal charge of 0. What about carbon? So carbon has 4 valence electrons. It doesn't have any lone pairs, so that's a 0. And there are 4 bonds around carbon. So carbon is getting 1 electron from each of those bonds. So it's got 4 bonding electrons around it. So 4 minus 4 gives us 0. And if we add up our formal charges, 0 plus 0 plus 0 equals 0, which is good because carbon dioxide is a neutral molecule. Cool. All right, let's keep going. So what about when we can draw multiple different Lewis structures for the same molecule? When non-equivalent Lewis structures exist, the best Lewis structure, so the one that I would want you to draw on a quiz, is the one with all the formal charges closest to 0. So let's look at carbon dioxide again. What are the other ways we could draw carbon dioxide? So our skeletal structure that we started with was, and then with our lone pairs on terminal atoms, we had 3 lone pairs on each oxygen, and carbon only had 2 bonds. So I took a lone pair from both oxygens to make double bonds. But what if we just took 2 lone pairs from one of the oxygens and made a triple bond? That achieved the same thing, right? So now we have we have a triple bond between carbon and one of the oxygens, and a single bond between carbon and the other oxygen. So carbon still has 8 electrons around it. It's still got a full octet. Our oxygens both have full octets as well. So those are valid Lewis structures, but they aren't the same. The bonding is not the same. So we want to see which one is the best Lewis structure. And that's going to come from the formal charges. So the formal charge on this oxygen in this version of carbon dioxide is 6. So valence electrons is the same. 6 minus, so there's only 1 lone pair, so there's 2 non-bonding electrons, and now there are 3 bonds. So our formal charge is +1. And this oxygen does the opposite. So this oxygen, we have 6 valence electrons. We have 6 non-bonding electrons because now we have 3 lone pairs. And we have a bond. So that's -1. So we've got formal charges that are not 0. And if we put the triple bond on the other side to the other oxygen, we just get the flip-flop version. So both of those have formal charges that are not all 0. But if we draw it this way, we can get formal charges of all 0. So we want the charges to be closest to 0. So this is the best structure for carbon dioxide. These other two are not the correct Lewis structures for carbon dioxide. Alrighty. What else do we do here? So a Lewis structure has a positive, or a Lewis structure with a positive formal charge on the more electronegative element is not stable. So if we were to draw, so this is the structure for boron trichloride that we used before. We liked it. It was 0 for everything. But how else could we draw boron trichloride? Well, we could take one of those lone pairs and pop it into a double bond so that boron has a full octet. So if we do that, then what happens? So boron has 3 valence electrons, and now it has, so it doesn't have any lone pairs still, but now it has 4 bonds. So boron has a -1 formal charge. Chlorine, on the other hand, chlorine had 7. It now only has 4 non-bonding electrons, 2 lone pairs, and 2 bonds. So that's a +1. So this is not as stable because we've got a positive charge on our electronegative element. And our electronegative elements, so our more, I should say more electronegative, our more electronegative elements is usually where we have that high electron density. So it's usually the negative end of our dipoles. So having a positive formal charge on there is not, it doesn't make any sense. So we don't use this structure either. So we want a Lewis structure, 1 with formal charges closest to 0, 2 with negative, or well, no positive. So we don't want positive formal charges on our more electronegative element. So those are 2 of our rules. What else do we have? When formal charges are equal in non-equivalent Lewis structures, so we have 3 non-equivalent Lewis structures like the one down here for, this is our cyanate ion, I think it's called. See, I don't even remember all of them. So we have 3 different structures here, and the formal charges all add up. So the formal charges all add up to -1 because this is the OCN negative ion. So these two, so this structure is definitely not the best because we've got a -2 in there, but these two are the same. So they have the same formal charges just on different atoms in our Lewis structure. So how do we know which one we want? This goes back to that previous thing where we don't want the positive charge on the more electronegative atom. In this case, we want the negative charge on the more electronegative atom. If there's a negative charge that we need to put somewhere, oxygen is more likely to carry the negative formal charge because oxygen has a greater electronegativity. So this is the best structure based on electronegativity and formal charges. So let me erase so that we can talk about this slide again a little bit. So here's our structure. So the thiocyanate, not thiocyanate, sorry, the cyanate ion has carbon in the middle because it's the least electronegative atom, and then oxygen and nitrogen are our 2 terminal atoms. So if we follow our steps here, we want to know the number of valence electrons and we want to draw the skeletal structure. So what is the number of valence electrons? We've got 6 from oxygen, 4 from carbon, 5 from nitrogen, and we've got a negative charge, so that means we have an extra electron. So we've got 16 electrons to play with. So if we put all of our electrons on our terminal atoms. Okay, so now we have 1, 2, 3, 4, 5, 6 lone pairs. So that's 12 electrons, and we have 2 bonds. So that's another 4 electrons, 2 in each bond. So that gives us 16. So this is correct. I'm just scribbling all over here, sorry. This is correct, but carbon doesn't have a full octet yet. So what can we do? So one way to fix that is this version right here, where we take 2 of oxygen's lone pairs and throw them in a triple bond between oxygen and carbon. And if we do that, then oxygen has a formal charge of 6 minus 2 minus 3 bonds equals +1. So that's where they get this from. And nitrogen with 3 lone pairs would be 5 valence electrons minus 6 non-bonding electrons, and it's 3 lone pairs, and then 1 bond, which gets us to -2, and that's where they got this from. So that's not great. So what if we do something else? So if we take 1 lone pair from each, we can put them like this. So there's a double bond and 2 lone pairs on each, on the oxygen and the nitrogen respectively. So double bonds and lone pairs the same on both. And that's going to give us formal charges of 6 minus 4 non-bonding electrons minus 2 bonds is 0 for oxygen, and 5 minus 4 non-bonding electrons minus 2 bonds is -1 for nitrogen. But oxygen is the more electronegative between oxygen and nitrogen, so we actually want to do this one instead, where our -1 charge is on oxygen and not nitrogen. So let me erase a little bit so we have more room again. Boop, boop, boop. Okay, so in this case, our oxygen had 6 electrons, 6 valence electrons, minus 6 non-bonding electrons, because it's got 3 lone pairs now, minus 1 bond, equals -1. And nitrogen had 5 valence electrons, minus 2 non-bonding electrons, and it's 1 lone pair, minus 3 bonds gives us 0. So we still have a -1 formal charge. We can't avoid it because we need a negative charge to add up to -1 on our polyatomic ion. But when we can't avoid it, we want it on the more electronegative atom. So we want it on oxygen. So instead of doing this nice equal sharing like we did with carbon dioxide, the cyanate ion, instead we take 2 lone pairs from nitrogen and make a triple bond to carbon and leave oxygen alone. Okay, cool. That was a lot, sorry. So I'm going to keep going and talk about resonance structures. So I'm going to stop here and start another video because I think I've talked long enough about formal charges. Let me stop.